A single train wheel weighs several tons, yet it rolls smoothly on the rails for decades. A single rail, stretching 100 meters and weighing over 6 tons, can withstand tens of thousands of heavy loads without deforming. How does the steel industry manage to create such extraordinary strength? Few people realize that to forge a rail capable of withstanding such immense pressure, metallurgy must follow a long chain of complex processes. Iron ore is extracted from deep within the earth, mixed with coke and other additives, then fed into massive furnaces at extreme temperatures. From there, the incandescent molten steel is refined and rolled with millimeter-perfect precision into its distinctive head, web, and base profile. It then undergoes heat treatment and is welded into continuous lengths, stretching for hundreds of meters, before undergoing rigorous laser, X-ray, and ultrasonic inspections. In this film, we will go inside modern steel mills to witness the transformation of raw ore into strong rails. The global market for rail steel. The railway industry is not just a vital link in transportation, but also a massive economic sector. The global market for rail steel was valued at approximately $15 billion in 2023, and forecasts suggest it could reach nearly $20 billion by 2032. These figures reflect the scale of investment flowing into railway networks, particularly in regions with rapidly developing infrastructure like Asia, and even in the United States, where modernizing over 225,000 kilometers of track is considered a strategic priority. From a production standpoint, the scale is even more striking. The world produces about 1.9 billion tons of crude steel every year. In the United States alone, steel mills maintain annual productions of millions of tons, with a significant portion shaped into rails for domestic use and export. These rails are not an ordinary product. They must endure more than 20 years while withstanding the immense and repeated loads of trains. In many ways, each rail acts as a lifeline of modern infrastructure, ensuring stability, safety, and efficiency across the rail network. Raw material extraction and processing. A rail's journey doesn't start in a factory, but deep within the earth. Its most important ingredient is iron ore, and to reach it, immense open-pit mines are carved into the landscape. Here, hydraulic shovels as tall as 3-story buildings and ultra-heavy-duty dump trucks work tirelessly. Each bucket can lift tens of tons of rock in a single scoop. But before the machines can move, engineers must first drill holes that plunge dozens of meters into the ground. Centimeter-perfect precision is required because these holes will be filled with industrial explosives, and the blasting itself is far from random. Each charge is carefully calculated so that thousands of tons of rock are fractured, but the ore inside remains intact. Once the dust settles, the trucks and shovels get back to work, hauling the ore to the primary crushing station. In some geological areas, extraction takes place underground inside reinforced tunnels. The ore is scraped, loaded onto conveyors or small rail cars, and transported to the surface. Machines provide the power, but people remain the brains of the operation. They calculate explosive charges, guide the machinery, monitor safety, and inspect each load of ore. Every ton that comes out of the mine is far more than just broken rock. It's the foundation of steel, and ultimately, of the rails that will transport trains safely for decades. Once the ore is extracted from the mine, it can't be used right away. The massive blocks of rock must first go through an essential step, crushing. Inside processing plants, powerful steel rollers and hammer mills work continuously, breaking down blocks weighing tens of tons into small uniform particles. The size of these particles is not an accident, it's tightly controlled. If the pieces of ore are too large, they won't melt completely in the furnace. If they are too fine, the mixture becomes unstable during mixing. Only when the ore reaches the precise size required can it be moved to the next step, where it is blended with coke and flux materials in enormous mixing chambers. Gigantic paddles spin relentlessly, ensuring that every grain of ore and additive is evenly distributed. This step may seem simple, but it is critical. It guarantees that the mixture's chemical composition is balanced, laying the groundwork for steel with the strength and durability a rail demands. From these carefully prepared particles, the transformation to steel begins, a process that will ultimately produce rails strong enough to support the weight of trains for decades. Steel manufacturing. When the ore has been finally crushed and blended in the right proportions, the journey enters its most critical phase, steel manufacturing. This is the very heart of the rail production process. Inside the plants, gigantic electric arc furnaces and blast furnaces roar at temperatures of over 1,600 degrees, hot enough to transform iron or an additives into a uniform flow of molten steel. Automated feeding systems measure each batch with kilogram-perfect precision, while thermal sensors and spectrometers constantly monitor the chemical composition. Heat-resistant robotic arms stir the mixture and remove impurities that rise to the surface. At this stage, alloying elements like manganese and chromium are introduced at the right time, enhancing the rail strength, wear resistance, and ability to withstand extreme loads. A modern electric arc furnace can melt over 150 tons of steel in less than an hour, but this power comes at a cost. The steel industry alone emits nearly as much CO2 each year as the entire aviation sector. This raises a difficult question. How can we continue to build the infrastructure the world needs while reducing the industry's impact on the environment? The result of this stage is molten steel of the highest quality, ready for the next transformation. Only when temperature and composition are kept under precise control can these steel backbones be created, strong enough to serve as the rails that will transport trains for decades. Shaping and forming process. After leaving the furnace, the molten steel is cast into billets and sent directly to the reheating area. This step is critical for stabilizing the metal structure before rolling begins. Inside massive heating chambers, the temperature is maintained at optimal levels, typically above 1,200 degrees. High-power burners work in tandem with infrared sensors that constantly scan every point on the billet surface, ensuring the steel doesn't cool too quickly. Even a slight temperature drop could harden the surface, leading to cracks or warping during rolling. Once stabilized, the billets move to the rolling preparation line. Here, enormous heat-resistant rollers, driven by robust hydraulic motors and gearboxes, begin to shape their length and cross-section. The system is programmed to refine the pressure and rotational speed for each pair of rollers, distributing force uniformly and preventing localized stresses. What makes this step remarkable is the seamless integration of mechanics and electronics. A central control computer collects real-time data from dozens of sensors and instantly adjusts the process. Every movement aligns perfectly, like the gears of a precision clock, producing billets that are elongated, flattened, and ready for the final shaping process. As soon as they leave the reheating furnace, the incandescent steel billets are fed directly into the rolling line, the final shaping stage before cooling. On a system of heat-resistant roller tables, the billets enter the roughing mill, where massive alloy steel rollers, with large diameters and smooth surfaces, press them with thousands of tons of force. The thickness is significantly reduced, while the length is stretched, preparing the billets for precise shaping. Next, the billets pass through intermediate stands, where the profile gradually takes shape. Here, the rollers are arranged in alternating positions, compressing and twisting the steel to evenly distribute stress and eliminate dimensional errors. In the finishing mill, rollers with specially designed grooves begin to sculpt the rail's classic I-shaped cross-section, a design that offers remarkable strength while keeping the weight manageable. Between each rolling stage, high-pressure water jets cool the surface, removing the oxide layer and maintaining temperature stability. Along the line, laser sensors constantly measure height, width, and straightness, sending real-time data to the central control system, which adjusts roller gaps and speeds with extreme precision. One of the remarkable features of this process is the ability to quickly exchange roller sets, allowing plants to switch between different rail profiles without stopping production. This step is decisive. It sets the rail's geometry and ensures each piece meets the required standards before moving to cooling and heat treatment. Heat treatment and welding. Under the intense heat inherited from the rolling process, the steel rails still glow red and contain significant internal stresses. Cooling and heat treatment are the critical steps that stabilize the product's backbone. Immediately after leaving the rolling mills, the rails pass through a high-pressure water spray system, where a dense mist envelopes their entire surface. The speed and volume of the water are tightly controlled to ensure uniform cooling over the entire length, preventing warping or cracking. After this rapid quenching, the rails enter the heat treatment zone, where reheating furnaces are precisely programmed to perform processes such as quenching, tempering, or annealing, depending on the desired mechanical properties. The combination of immediate cooling and subsequent controlled heating not only enhances strength and durability, but also ensures that the rails retain their distinctive I-shaped profile, with sharp edges and clean lines. This step is what guarantees that the finished rails can withstand the enormous repeated loads of rail traffic, while maintaining long-term stability. By carefully balancing temperature and time, engineers give each rail the resilience it needs to reliably serve for decades on some of the world's most demanding infrastructure systems. Fresh from heat treatment, the rails move directly to the welding line, where individual sections are joined into continuous lengths. Guide rollers work in tandem with laser sensors to ensure the rail ends align with absolute precision. A high-power arc welder releases intense heat, melting the steel edges while hydraulic pressure forces them together into a seamless bond. Immediately after, an automated grinding system smooths any excess material, leaving the weld surface perfectly level with the rail body. The entire operation is supervised by a central control system, which constantly refines variables such as temperature, pressure, and timing. The result is a joint so strong that its durability matches that of the solid steel itself. This process of welding long rails transforms shorter segments into continuous tracks stretching for hundreds of meters, rails that will carry high-speed trains with minimal vibration and with a strength built to last for decades. Quality control. The finished rails move to the quality inspection area, where every detail is scrutinized with precision. Optical sensors and high-speed cameras scan the entire surface, capturing images at a level that can see through the slightest scratch. The data is then processed by advanced image analysis software, detecting any deviation in shape, color, or texture. At the same time, ultrasonic devices and X-ray scanners probe deep inside the steel, ensuring there are no hidden defects, such as internal cracks or gas pockets. To complement these scans, randomly selected samples are subjected to rigorous mechanical testing. Powerful machines stretch, compress, and press the steel, while hardness testers measure resistance to deformation. All results are carefully recorded and stored, allowing each rail to be traced back to its production batch. Only those that meet the entire set of criteria earn the seal of approval, confirming they are fit for service. Once certified, the rails are cleared for packaging and distribution, ready to be shipped to construction sites, where they will become part of the railway lines of tomorrow. Transportation and installation process. From the factory, the rails are transported to the construction site on oversized trailers, securely fastened to prevent shaking or bending. Once on site, the steel sections are unloaded by cranes and specialized forklifts and placed in the designated preparation area. From there, the work that requires human skill and experience begins. Installers follow structural drawings to position each rail using laser levels and surveying instruments to control alignment and slope. Temporary joints are first secured with bolts, before being permanently welded or clamped. Throughout the process, workers constantly communicate via radios to synchronize their actions and ensure perfect connections. Machinery primarily assists with lifting and holding the rails, while fine adjustments, alignment, and finishing depend almost entirely on the skill and coordination of the installation team. It is this meticulous work that determines the stability and safety of the entire rail system for decades to come. Under protective coatings and solid welds, each steel structure is the result of hundreds of hours of work, combining the power of machines with the hands of skilled workers. From the mine to the construction site, each step contributes to creating the backbone of bridges, factories, and towering skyscrapers. By looking at this journey, steel reveals itself to be more than just a material, it is the foundation of modernization. If you like this video and want to discover other impressive manufacturing processes like this one, don't forget to like, subscribe, and hit the bell so you don't miss a thing, because what comes next will be just as fascinating and interesting. There was a time when computers filled an entire room, then innovation made them small enough to fit on a desk. Today, they've transformed into portable machines that fit on your lap, and now laptops are smaller and more powerful than ever. Discover cutting-edge technology and be amazed by the power you can hold in your hands. Every step of manufacturing hides incredible precision, and what you're about to see might just change the way you look at electronics. At the heart of this computer lies the motherboard, the true brain of the device, built from a sophisticated printed circuit board. A network of copper lines forms the pathways through which all electronic components communicate. An automated machine applies a precision stencil, then deposits solder paste on specific areas of the circuit. A high-definition camera captures images and sends them to an intelligent analysis system, which detects any anomaly such as misalignment or missing material. And if you really want to understand how modern technology shapes our lives, subscribe and hit the notification bell. It helps the channel and ensures you won't miss any content as fascinating as this.
If everything check out. The board goes through 15 industrial robots.
Each places up to 150 components in just 30 seconds. The board then passes through a specialized oven where the paste melts, bonding each component to the motherboard. Another visual inspection ensures the central processor is properly soldered and that nothing is misaligned. After a functional test, the board is set aside to make room for manual assembly. Experienced technicians mount the upper part of the laptop, known as the display panel. They apply a protective film to a 15-inch LCD screen, then connect the main cable to the motherboard. The screen is integrated into a frame equipped with a webcam and microphone. A lower cover with an antenna is then fixed, and the connection cable is positioned inside. The webcam and microphone are installed, followed by two sturdy hinges that connect the screen to the rest of the computer. The Wi-Fi card is also put in place. All components are then concealed under a sleek top cover, and a slim metal frame completes the assembly. Next comes the lower part of the laptop. The technicians attach the upper cover along with the precision touchpad. Then they add the left and right speakers. The motherboard returns to the line, where a computer-assisted milling machine cuts precise openings to install the cooling fans. A gaming laptop generates much more heat and therefore requires two powerful fans. Once secured, the motherboard is installed, with connectors carefully cleaned and dried with compressed air. Then comes the installation of the memory module, Wi-Fi and Bluetooth, and the SSD drive, not to mention the high-capacity battery, essential for this type of machine. Finally, the keyboard is installed into a dedicated opening in the upper cover. A laser engraves the characters, and an automated machine tests the main functions. A specialized team then checks virtual reality performance, screen display, keyboard lighting, and of course the durability of the keys. Have you ever taken a moment to wonder how those little colorful bricks you played with as a child are made? Lego has been around for more than 80 years and has become an essential reference in the toy world. But have you ever thought about the incredible process behind each brick, from mold design to plastic injection? This entire journey is a true technical adventure worth seeing. Today, we dive together behind the scenes of Lego manufacturing. From the very first sketch to the final packaging, every step is a blend of precision and meticulous engineering. Pay close attention, because some stages are so fascinating they almost look like the work of a master craftsman. Lego bricks come in a huge variety of shapes, from the classic 4x4 to far more complex pieces with specific functions. But where do all these new shapes come from, and how are they imagined? That's where Lego designers come in. Over 200 creators from diverse backgrounds such as industrial design, architecture, and graphic arts. They combine creativity, technical expertise, and advanced digital tools to bring their ideas to life. It all starts with a brainstorming phase, where ideas take shape through sketches or physical prototypes. Then, these concepts are modeled on a computer to guarantee perfect compatibility with other bricks, because interconnection between every piece is at the heart of the Lego experience. If you find this process as fascinating as we do, remember to subscribe to the channel and activate the bell. It really supports us and allows us to bring you even more quality content. Once the design is approved, it moves on to the next step, mold creation. Each new piece requires a specific mold made with extreme precision using specialized machinery. It begins with a master metal model based on the 3D file. This model is then used to form the mold insert, made from an ultra-resistant steel alloy. This component is machined using EDM technology, which cuts with incredible precision through electrical sparks. The insert is then set into an aluminum base that channels molten plastic through the mold cavities. But before being used, every mold undergoes rigorous testing. Through a trial injection, the quality, shape, and consistency of the result are verified. Once validated, the mold is installed in a plastic injection machine that brings the bricks to life. Plastic pellets, often ABS, are heated and injected into the mold at high pressure. They quickly solidify, giving birth to the final brick. The pieces are ejected, then carefully inspected and sorted according to shape and color. Some bricks are made from single-color plastic, while others use multiple colors thanks to a highly sophisticated co-injection system. Even elements like wheels, doors, and minifigures are made through this advanced injection process, sometimes followed by extra steps such as painting or printing. Then comes the finishing stage, where the sprue, the small excess of plastic, is removed using precision cutting and sanding techniques. After that, the final details are added: logos, patterns, or other essential markings. Each brick is then automatically sorted and packaged, often in bags or boxes, ready to be shipped worldwide. LEGO also carries out extremely strict safety tests to ensure every brick is non-toxic, strong, and safe for children. This high level of quality control and technical mastery is what has allowed LEGO to become much more than just a toy. It's a universal symbol of creativity and limitless building.